morning, ladies and gentlemen, and welcome to the Hydrogen Fuel Cells and Batteries Group exhibit. You're here with me today at the Technical Forum. I invite all of you to please get comfortable, grab a seat, enjoy a coffee, juice, or water while you watch our next presentation. So our next topic is LADOG, a fuel cell-powered municipal vehicle. And I think actually if you look to the back of the room, it's the bright orange truck parked back there. But now I invite you to turn your attention back to the front of the stage while we welcome our speaker. Here with us today, we have a scientist from the Fraunhofer Institute for Solar Energy Systems, Mr. Stefan Keller. Welcome.
Yes, Helen, thank you for this nice introduction. Ladies and gentlemen, welcome to my talk. I would first like to introduce to you the institute I'm coming from. It's Fraunhofer ISE. We are located in Freiburg. It's in the south of Germany. And as you see on this picture, it shows the main building of our institute. We almost have always nice weather. This is also the reason why we are a solar institute, so that fits quite well. However, if you have a large amount of solar energy, you need to store it. And this is where the hydrogen comes into the game. And this is also why we have a department within our institute who operates on fuel cells, and we're expert in fuel cells for more than 20 years now. What we do is characterizing local effects on stack and cell levels. We do investigations, lifetime analysis of materials and components, lifetime testing, balance of plants characterization. We have 2 climate chambers where we can do climate tests. So all the necessary thing you need to characterize your fuel cell. Today, I would like to introduce to you a special project which we did together with the partners. It's called ELAN, the project. And what I want to show you is why we did this project, what the motivation is, what was the vehicle we choose in this project, and what the contribution of the Fraunhofer Institute was. So the motivation why we did this project is summarized with this picture. So you maybe followed the news. In Germany, we have a big problem, not only in Germany, with pollution of air out of exhaust gases, especially from the transport sectors. We have a lot of dirt air, we have CO2 emissions, we have noise, we have pollutions, especially in the metropolitan areas. And you may know it from other metropolitan regions, like in Asia, for example, or also in the United States. So this is a very common problem, air pollution due to exhaust gases from the transport sector. So here I have some slides, the CO2 emissions from this sector. We see here the reduction of CO2 for Germany. The goal is to reduce it to approximately 80-90% until 2050. We see here different sectors, for example, the energy sector, the industry sector, the home sector. And what we see is that for all sectors, the way we are on is quite sufficient. So sometimes a little bit more ambitions would be preferable. But what is something special is the transport sector here. You see that the reduction of the CO2 emissions is almost not visible. And this is what this sector is different compared to all the other sectors. So here we have to address in special to reduce the CO2 emissions in this sector. As in transport, we need to do something. Another thing is air pollution. As I mentioned, not only an issue in big metropolitan regions, for example in Asia, also here in the European Union. There are different studies. This one I just grabbed from the news, saying that 500,000 people are killed every year in the European Union by air pollution. And here the transport sector is also a quite big contributor. You may have followed it in the news. There was a very interesting, a very landmarking, you can say, decision by a court, a very high court, which said that in general it might be possible to ban diesel engines from German cities, and this of course affects the market of transportation, the market of automotive applications, but also heavy-duty applications very much, as it might be that you really are not allowed in a few years to drive with your diesel engine into a city. So this is a big challenge, a big problem. Pollution, CO2 emissions, air pollutions, maybe driving bans in the transport sector. And here we try to provide a solution, at least a part of a solution. You see here a small truck, a small municipal vehicle. And what we did within the project Elan is turning this vehicle from diesel into electric. The vehicle itself is specially designed. It's, as I said, a small truck. It can be equipped with many different tools, for example, for mowing, as you see it here, but also for snow removing or for cleaning streets and pedestrians. The company who builds this truck is called LADOG. And LADOG is a German abbreviation, and it means leichte Arbeit durch ordentliches Gerät. And this describes the machine very well. Translated to English, it means work is easy if you have the neat machine. So something very nice, you can say. Now, the basic idea of the project Elan was very simple. We want to remove the diesel engine and the hydrostatic drive, and we want to replace it by an electric motor, a fuel cell and battery combined system to really have an absolutely 100% electric drive train. Therefore, we needed the right partners. We partnered with industry companies, especially to mention here Elring Klinger. They are also located in the south of Germany. They provided the battery packs and the fuel cell. They are also here in this hall 27 on booth E54. Another partner was the company Heinzmann. They provided the electric drive system, so the electric motor and the motor converters. They are also here on the Hannover Fair in this hall on booth K42. Another partner was Fronius. They are located in Austria, and they assembled the fuel cell stack to a complete system so that we have an overall fuel cell system. And of course, the vehicle manufacturer LADOG, who provided the vehicle and did all the vehicle integration. And we, the Fraunhofer Institute, did the accompanying scientific work by modeling the propulsion system and analyzing the load profile which we needed to supply. This is how the system within the vehicle looks like. So we have first the hydrogen tanks here, 4 vessels, each at 350 bar. We have altogether approximately 3.6 kilogram hydrogen. This gives you an amount of approximately 65 to 70 kilowatt hour electrical energy, so comparable with a really large battery pack. We have 2 fuel cell systems, each providing approximately 10 to 12 kilowatt of usable energy. Each fuel cell system has a 100 cell stack integrated. The stacks can be assembled in different or for different cell numbers. Here we chose 100, but it can easily be adapted to other applications with higher or lower power demand. We also integrated 2 systems of these as we want to address additional applications. One of these systems, for example, fits very well a forklift application so that we can use the propulsion system here, parts of this propulsion or energy supply system in other applications. This is also true for the battery pack. The battery pack within this vehicle consists of 9 battery modules. Each module has 7 cells integrated, and these 7 battery cells have a standardized size or format. It's a plug-in hybrid electrical vehicle 2 format. So here we have also a kind of standardization and a modular approach. And last but not least, we have an electric motor. This one was designed by the company Heinzmann and especially adapted for the relatively low voltage of 80 volt to get an extra power or an extra level of safety to keep the voltage low. And this was also to address additional applications as the logistic transportation sector uses these relatively low voltages. So the goal in this approach was to provide a modular propulsion system that each element can also be used in additional applications to simply realize something that produces more numbers, more counts than only addressing one single application. The advantages of this electrical driving system is simple. You have no noise, no pollution, and therefore you also do not have to fear driving bans. Thanks to the hydrogen, you have a fast refill. and you're back at work in a few minutes. You don't have to recharge the battery over a long time. And the performance is comparable with the diesel-powered conventional system. This was one goal of the electric motor, that it has the same power and torque as the diesel system. And the low voltage design gives you extra safety, easy maintenance, and it is designed to also address other applications, like, for example, logistics applications. And what we did, our contribution of our institute, was modeling the fuel cell and the battery. The fuel cell, you see it here on the left side, was a physical-based model. We have the main processes taking place within the fuel cell integrated. For example, the energy and mass momentum conservation equations, and we also integrated the water management to have the main effects within this model. The same is true for the battery model. We have here an electrical circuit model with temperature and state of charge dependent parameters that we can model the behavior of the battery and of the fuel cell quite exactly. What we also did is enhance the fuel cell model to a complete fuel cell system model. So we also adapted components like humidifier, like air supply, and the hydrogen recirculation loop, you see it here, and the cooling to get the feeling and to get the ability to model the complete fuel cell system and not only the stack itself. And with these models and approaches, you can do a lot of things without the need to really build up the complete system. So for example, you can do a dimensioning optimization, you can optimize the control strategy, you can simulate different temperature ranges, for example, how the system will be performing, and you can predict the system efficiency. And here I just want to show you short 2 slides. This is the result of the system efficiency prediction. You see here on the one side the voltage of the fuel cell stack. The higher the load you draw, the less the voltage goes. This is simple normal behavior for a fuel cell system. And the system efficiency is given here on the red line, so it peaks at part load at slightly above 60%. And at full load, nominal load, where you have these approximately 10 to 12 kilowatt per system, it has still a little bit above 50% efficiency. Another thing you can do with the simulation is, as I mentioned, testing in which temperature range, for example, how the system will behave and perform. And here we have a chart showing these very interesting curves, you can say. The voltage, the mean voltage of the battery at 2 different temperatures level. Red is at 20 degree, blue is at 5 degree. And we have the state of charge development over time for a given load profile, also for 2 different temperatures. So these are 2 examples what we can do with simulation of these systems to predict how it will perform at different operating conditions. Short summarize, what we did within this project is the electrification of a municipal vehicle. This we did with a modular approach of the fuel cell system, and also the battery modules are modular. We have a low voltage architecture addressing further applications and putting some extra safety inside. The advantage is that the performance of the vehicle is quite similar to the normal conventional diesel version, but you have a clean and a low noise operation without pollutions, and you don't have to fear any driving bans. And you have both advantages of the hydrogen and the battery world together. You have a fast refill, but also an efficient operation. I would like to thank the Ministry of Economics and Energy on the German side, as they partly funded the project, and also on the Austrian side, the Research Promotion Agency. And this was also a nice example for a German-Austrian collaboration within this project. I would like to give you a hint for another talk tomorrow. A colleague from mine from our institute, Dr. Robert Arling, will have a presentation tomorrow at 11:20. And of course, you are welcome to our booth on C58. But there's one last thing. So it's one thing to speak about slides and showing slides and everything. The vehicle itself is just standing right over there. So if you want to have a closer look on it, you're also welcome to get on the vehicle and see the hardware itself. It is capable of driving. Unfortunately, we are not allowed to give test rides here on the fair, but still we have it in hardware here and it's operating. Thank you.
And thank you so much for that talk, Mr. Keller. It's a bit of a shame you don't get to drive around the vehicle in the fairground. I do a lot of walking day to day. I feel like a small municipal vehicle would be great. At this point, do we have any questions from the audience? Great, I'll come down to you.
Hi, my name is Xiaodong Jia. I'm from China. My question is, compared with the conventional electronic vehicles like this size, so how about the cost, the operational cost, like per kilometer? I mean, is there, of course, I won't expect any advantage compared with traditional electronic car, but actually, at least some comparable level of the cost would be nice.
Yeah. Of course, the answer is very hard for me at the moment, as within this project, it was simply more the technical focus. So we wanted to see if it is feasible to do or not. And it is very hard to estimate the costs. If a customer says, I want to buy this vehicle with fuel cell system and batteries, how much does it cost? So this is hard to answer, as it was especially designed and only one system, one vehicle. And of course, costs are very dependent on how much you order. Also at the moment, it would be very difficult for the partners, for example, to supply hundreds or thousands of these vehicles, as they are small companies and it's more to prove the feasibility of the systems. So what we know is that the manufacturer of the vehicle, LADOG, the company, said they might be able to have an additional of 20 to 30% compared to the conventional vehicle. This would be something which the customer would accept to have the benefit of clean and low noise operation. But we are at the moment, of course, quite far away to achieve this, but this was something, or would be the goal, to have this system realized and to bring it into the market and to really can sell it. So that's unfortunately the only answer, or the closest answer I can give you to this question. Mm-hmm.
Okay, thank you for that answer. Are there any other questions at the moment? Okay, so I just briefly, you mentioned that there are some other applications. You mentioned a forklift. Naturally, as a Canadian, my first thought went towards snowplows. So I imagine that you'd be able to put a snowplow on the front of this, but how would it behave in super low temperature? You mentioned that you had been testing down to 5 degrees. What sort of performance can you expect at quite low, like say minus 20 or minus 30 Celsius?
As long as it is operating, it's probably no problem. So the system is prepared for freeze start capability, so that you can even start it at low temperatures, below 0 degree, below minus 5 degree. We did not exactly test it in this system setup, how low the temperature can go. The project partner, LADOG, did with this stack assembly, so as this is the most challenging part within the system, tests down to, I think, minus 20 degree for freeze start capability. However, we did not realize it in that point of the project within this vehicle there. So the stack itself, the system is prepared for freeze start capability. The stack assembly in a smaller version is tested down to minus 20. Within this vehicle exactly, we did not prove it at that low temperature.
Okay, great. This is good information to have. So if anyone comes up with any other questions, I'm sure they can drop by the booth. They're located at booth C58. And you'll be here for the rest of the fair?
Yeah.
Okay, great. Well, thank you so much for your attention, and thank you for that presentation.
Thank you.
At this point, I'd like to invite all of you to remain here. Our next presentation is going to continue on in the transport sort of theme. We have urban commercial transport towards a sustainable traffic and mobility system, and we'll be starting with that in really just a moment. Thanks so much.